Hello everyone, my name is Zubin Kane and I have decided to use this presentation as an opportunity to present about my field of research. Neuromorphic computing is one of the newest advancements in computational technology, so let's sit down and explore this fascinating departure from von Neumann architecture. We have all probably heard of or worked with neural networks. They are large groups of interconnected neurons which can provide the abstraction of data necessary for techniques such as reinforcement learning. Neuromorphic networks are a bit different than normal neural nets, so let's start by examining what a more traditional neuron looks like. Traditional neurons have two main parts. First, a value, which is either an input or the sum of weighted inputs. A neuron also has outputs, each with a specific weight which determines how impactful its predecessor is to its successor. The value of a neuron can be limited, and these values can be treated as continuous or discrete. Neuromorphic computing is a bit different. It takes inspiration from biology, where neurons pass information by spiking at various intervals, rather than passing specific analog values. This makes neuromorphic computing much closer to cognitive processes than traditional neural nets, which are really just abstractions that can enable computer learning. Like with traditional neurons, a spiking neuron also has two parts. The neuron contains an electrical potential, which enables firing, during which synapses briefly have a high electrical potential. Spiking neurons can convey information through the rate at which they fire, as well as through the timing of the firings. Now, when drawing diagrams, a neuron is characterized by a threshold and a voltage. The voltage represents the electrical potential inside the neuron, and the threshold represents the electrical potential needed for the neuron to fire. A synapse is characterized only by its weight, which determines its significance as an input, similar to with traditional networks. As weighted input synapses fire, they raise the electrical potential inside the postsynaptic neuron. It could take a while for the neuron to accumulate enough electrical potential to fire, so we also need to take into account decay, in that the electrical potential decreases over time, though this often happens fairly slowly. When the electrical potential of a neuron reaches that neuron's threshold, the neuron fires. This causes the electrical potential in the neuron to reset. Really, it's being used up in that it causes the electrical synapses to spike. The brief transmission of that energy to postsynaptic neurons. Let's look at an example. This network is pretty simple. Only 3 neurons. This is a basic type of spiking network where potentials, thresholds, and weights are all integer values. All of the thresholds are 1, and we can assume that all weights are 1 since they are all unlabeled. The electrical potential of both inputs here are variables, x and y, while the electrical potential of the output neuron starts at 0. Suppose x is equal to 1 and y is equal to 0. The potential of the x neuron top left is the same as its threshold, so it's going to fire. Both of the other potentials are 0 though, so they're inert for now. The x neuron fires. Remember, this resets its potential to 0, and that potential is conveyed along the output synapse to the rightmost neuron. After the x neuron has fired, now the output neuron has the potential equal to its threshold, so it's going to fire too. To keep the order clear, we can think of this happening one time step after the x neuron fires. So now the output neuron has fired and its potential will reset to 0. We have one output spike, and otherwise the network is completely inert until more inputs are provided. This network is so simple, in fact, that its behavior corresponds to a basic logic gate. As long as at least one of the inputs is equal to 1, the output will spike once. And that is why this network corresponds to an OR gate. It might be a little odd seeing it in this form, but the behavior is simple enough to understand. Let's explore a bit further though. What do we need to change in order to convert this OR gate to an AND gate? How can we make this network spike only when both of the inputs spike? It turns out all we need to do is change the threshold of the output to 2. This way, both the x neuron and y neuron must spike at the same time for the output to spike. If they spike at different times, the potential in the output neuron will decay and it won't reach the threshold. In fact, the 2 can be generalized to n, the number of inputs to the AND gate. Well, now that we have explored the basics of spiking networks, let's look at some applications. One of the biggest applications of neuromorphic networks comes from their derivation of biology. Since we have computer chips and logic that function analogously to human brains, we can simulate and learn about cognitive functions. This application has a lot of potential to be explored in the years ahead. A much wider application of neuromorphic technology is in the overall world of computing. Neuromorphic chips use orders of magnitude less power than von Neumann architecture. These chips are also fully parallel. Any number of algorithms or operations can be happening simultaneously, rather than relying on threads, operating systems, and CPU scheduling. There has been a recent push to implement commonly used scientific algorithms on neuromorphic hardware to achieve those low-power, fully parallel aspirations. While many of these implementations are primarily used in a research capacity, it may not be long before they are integrated as part of high-performance computing clusters, tasked to perform specific, massively parallel operations. There are two main considerations when developing or re-implementing a scientific algorithm for neuromorphic computing. First, we want to design fully parallel algorithms. Although not necessary, it is important to take advantage of this feature of neuromorphic hardware when possible. We also want to design linearly scalable algorithms. This is aided by parallelization, but still requires some extra care and thought. I'm going to leave you with a slightly more complex example to think about: sorting. We have non-comparative sorting algorithms such as radix sort and bucket sort capable of sorting in a runtime of big O of n. Now, using fully parallel neuromorphic architecture, we have the potential to sort n numbers in big O of 1. Every number sorted at the same time. Well, we've come to the end of our time. I hope you've enjoyed this presentation, but most of all, I hope you learned something about neuromorphic computing and where this technology might be taking us in the near future. If you have any questions, feel free to ask them down below, and I'll do my best to answer them. Thank you very much.